the order in the slides. It's
okay, Mark, and then impair. Okay, it looks like he has one slide, so I would just leave this.
That's
and let
perfect.
the guy cycle.
All right.
Okay, Mark, go ahead, and I'll set my timer.
Okay. Hello. My name is Mark Corbin. I'm from Embercosm. My poster, Optimized Soft Float Routines for RISC-V, covers my project, which has been inspired by the long-existing, highly optimized soft float routines which exist in libgcc for ARM platform. At a simplistic level, if you look at single float addition for ARM in the libgcc object files, it's a program of approximately 220 lines of assembly code, and that compiles down to about 592 bytes. RISC-V uses the standard macros that are available in libgcc for soft float, and they expand out to about 590 lines of C code, and that compiles down, in this case, to 860 bytes. So there's about a 31% code saving in the RISC-V routines. The goals for this project are to try and produce better performance and code size for platforms without floating point hardware and for all soft float routines. My poster will cover the hardware environment, the build environment, the production of a test benchmark framework, baseline benchmarks on the Sci-Fi Hi-5 Unleashed board, verification to the IEEE 754 standard, and cover the progress of my work so far in developing optimized routines. If you're interested or have any questions, please come and find me afterwards. Thank you.
Thank you. Thanks.
Did you say I had a timer somewhere?
Okay, I got your timer.
All right, okay.
Go.
Yeah, hi, my name is Simon Davidman from Imperius. What I'm going to talk about is verification techniques around RISC-V, and I'm sure I'll forget later, so come and see the poster and come and chat to me, and I'll be hovering outside for that. So the first thing that we have is a simulator, and what the simulator does, it basically is the simplest usage of our technology. Basically, you put ELF files in it, and you can run it, with debuggers. And it's currently up to date to the current specs as of last Friday, which is the full ratified user, the ratified privilege, the vectors, and the bit manipulation stuff up to, I think, 4 o'clock on Saturday afternoon. So it's a full implementation of all of the specification that's sort of stable out there. And it's available on GitHub. You can just download it. And it's actually used in the compliance group and available from the bit manipulation group as well. And what we have is a flow in our products. We're a commercial company. We sell tools as well. And we have a flow for sort of timing-driven add-in custom instructions with a variety of different tools. There is automation in there, but not to magically create instructions. And so there are a variety of tools which allow you to do it, so you end up with a full simulation technology at the end. And the last slide is we're also doing verification. We have a demonstration of this also on the open hardware stand where we're running our reference simulator against RTL. It's actually a RISC-V core in there, and it uses a random instruction stream generator, open source stream generator in there, so you can get verification of your design. Thank you very much.
Thanks, Simon. Cesare, you want to use the clicker? You can go ahead. Thank you. Go ahead.
This is a proposal for an API that will allow RISC-V applications to run in a zero trust model. So here is what it looks like. You keep your system separated in different containers, and you map all the hardware resources in the core and outside the core to these domains. And then based on the flow of the application, automatically the system switch in the right security domain. This is an evolution of the concept we know very well with trust zone, where you expand to multiple zones. Here is how it looks like. All the zones are binaries, so no need to code there. They come together with the kernel that makes this possible and the policies, which are defined in a flat file. And then there is a configurator piece of the toolchain that creates the flash image that you put on the system. And so here is what the system looks like. We have a demo downstairs if you want to see it. So at the hardware level, you have UMode plus PMP. Then you put this nano kernel, this enabler, which is called multi-zone. It's open source, freely available on GitHub. On top of that, you put your zones that are mapped to different parts of the system. All of this is running downstairs. You can check the Wolf SSL boot or the other core boots, and you can see the demo.
Excellent. Okay. Your presentation, Vladimir, should be right in there. Okay. Serve it up.
Okay, hi, I'm Vladimir from the University of Bremen, and at my poster I present to you our RISC-V based virtual prototype that we've built at the University of Bremen. So we provide a 32 and 64-bit RISC-V core with almost all standard extensions. It's implemented in system CTLM and is available open source under MIT license. Key features of the VP include software debug capabilities using the Eclipse IDE, support for the Linux operating system and some other operating systems, and also support for simulation of multi-core platforms. In addition, we have verified our VP using coverage-guided fuzzing, and we use our VP as platform for software verification by integrating concolic testing techniques. Okay, that's it. Thanks.
Awesome. Okay.
Hello, I'm Tobias Kaiser from the Mixed Signal Circuit Design Group at TU Berlin. What I'm interested in is how instruction stream properties map to energy consumption in SoCs. This is of interest if you want to look at microarchitecture, implementation and circuit level design of low power SoCs. And what I do is I have a collection of sample program code that I'm running in 2 simulators, in an instruction set simulator and in a gate level simulation. And then I want to figure out what is the connection between the numbers, the simulated energy and simulated cycle count, and the operation vector, which is generated by my instruction stream simulator. Yeah, and then I'm using the method of least squares to figure out the relationship. The result is, we have those linear maps, and well, we have some more numbers at the poster, and if this is interesting, please feel free to come to my poster. Thanks.
Thank you, Tobias. Kurt is up next. Go ahead, Kurt.
Hi, I'm Kurt Keval from MIT. I'm working with a multi-university consortium on Project Zeno, primarily housed at the ASCS lab at Boston University. We're interested in HPC and HTPC designs like Goblin Core 64, RV64, RV128 designs with extended memory address spacing like XBGAS. If you also have interest in this research space, come and grab me. We could possibly give you an account on one of our cool resources like the ZWolf, where you can do your cluster design and benchmarking.
Kurt, whoa. Olaf, your slide should just be able to advance.
Hi, I'm Olof from Camcom. So any company working with RTL design tends to build up sizable IP libraries, and then they want to reuse them, and they invent some tickle scripting, and that makes it possible to reuse, and then they need to work with a new tool, and then they need to add some more scripting, and suddenly there's just one person in the company who knows how this all works together. So if you're an engineering manager, don't let your engineers do this thing, tell them to use USOC. If you're an engineer, ask your manager for like 6 months to do this tooling and then use FUSOC and take a 5-month vacation. I can tell you how.
That's awesome.
Hello, I'm Chris from University of Manchester, and in my poster I will talk about MaxineVM. So MaxineVM is a JVM written in Java, and it integrates many compilers, including template compilers and optimizing compilers, and along with many memory implementations, since we ported the MMTK on MaxineVM. And since the last 6 months, we have been integrating and porting into RISC-V, which is really useful because you can edit MaxineVM code with IDEs, and in the JWorking group, where we actually propose extensions for RISC-V and JVMs, it's very useful to experiment very fast. In this poster, however, I will talk about some tools we developed during the porting process of MaxineVM to RISC-V that academics can use to teach the students about RISC-V and to follow the code flow from Java code down to RISC-V. And we also implemented extra tools which allow to actually take the code that's being generated and run it on QEMU. Thank you.
Okay, Andreas.
Okay. Hi, my name is Andres. I am from Galileo University from Guadalajara. My team, developed this open source and education-oriented simulator. It was designed to be used in different courses like compilers, machine instructors, or even assembly programming. There is a link for more information. Muchas gracias. Thank you very much.
Thank you. Ben, you're up next.
Can everyone hear me?
Yes.
Excellent. So I'm Ben. I'm here from the University of Bristol. We are developing an alternative crypto extension for RISC-V that is not based on the vector extension. It's an embedded profile extension designed for devices that need to consider timing and power side channel analysis. We've had some positive early results, but we really need some feedback at this point. I'm very happy to discuss things like power performance, area, and more importantly, code density, but only if you come and see the poster. Thank you very much.
Thank you, Ben. Okay, next up is Francesco Menicelli. Maybe?
Hello, everyone. Yes, Francesco Menichelli from...
That's what I said.
Yes, exactly. I was confirming. I am presenting a work done at the university, at the digital group at University of Rome La Sapienza. It is in this work, it is the first porting of the approximate memory support on Linux operating system for RISC-V architecture. Just a few words of introduction. Approximate memories are memories in which circuit level or architectural level techniques have been implemented in order to reduce energy consumption at the expense of rising error rate. They are supposed to be used by error-tolerant applications, which are applications which can allocate data in approximate memory if they can tolerate a degradation of output quality. At the poster session, we can discuss about our implementation, and we can show how it is currently running on a C5U virtual machine emulated in QEMU. We also have an example as a case study, an implementation of H264 encoder using approximate memories for frame buffers, and we can show the degradation of output and how this can be exploited. Thank you.
Thank you. Okay, Rick, you're up.
Can you hear me? Yes, I know you can. We were worried about some out of order execution there for a second, so we do have them in the right order. So I'm Rick O'Connor. I'm with the Open Hardware Group. You've already heard about the Core 5 family, so we have a Core 5 table out there in the reception area. We'll have two different demos on there. One is the NXP board, the Vega NXP board, slightly shifted with the Core 5 core. It's got a RISC-V core in it. And as Rob said earlier, they've shipped like 2,000 or 3,000 of these things already. It's very cool. And then this proof of concept demo that we're running for our verification environment. So this is a cloud-based System Verilog simulator running in the cloud from Metrics. And the demo was co-developed between Metrics and Imperis, running random instruction generators, directed tests, and the compliance suites validating a RISC-V core and comparing the results to a golden model. So come and see us at the table.
Hello. My name is Sandra Pinto. I'm from University of Minho in Portugal, and this work was done in cooperation with RISC-V. This basically describes the first fully functional software stack for RISC-V, for developing secure RISC-V architectures, and we basically are using the multi-zone as the underlying infrastructure for providing multiple isolated execution environments. On top of multi-zone, we run several software components, a secure version of the free RTOS, and also a secure TCP IP stack, Pico TCP, and an embedded crypto library, Wolf SSL. And we have basically a demo that shows, a demo that shows all of these pieces working together, okay? That's all.
Congratulations.
Hi, I'm Arvind Prakash from Binghamton University. This work is a part of the DARPA SIT project. This is in conjunction with Lockheed Martin. In order to understand software, if we have the source code, that's pretty it's more well defined. You can tune the compiler, make sure that you have somewhat well behaving code. But that's not really the full picture, right? Because you have binaries, and eventually we are going to run into binaries because that's where the money is. And when you have binaries, there's a necessity to understand the binaries, and that's what this poster is all about. We talk about the different challenges. We have released a binary analysis framework for IDA Pro, a RISC-V binary analysis framework. The big picture now is that the binary analysis framework generates the tags and makes sure that the software has enough information to verify that it's being well behaved. That goes into the underlying mechanisms, which then perform the enforcement. So the poster itself will talk about the challenges and how we tackle those challenges and what we have so far. So come see the poster. Thank you.
And just so everybody knows, the posters are adjacent to where all the tables were set up. Oh, out of order again?
Hello, I'm Sebastian from Silex Inside, a company in Belgium. So I'm going to present today the security enclaves. So the goal of the security enclave is to separate by hardware the security task done in the enclave and the rest done on the host CPU. Basically, the idea is that if you have any TPM or secure element in your system, that this IP is basically replacing it, integrated into the chip. So the IP will handle the secure boot of his own code and also the code of the host. It will handle secure key generation and also secure key storage in Flash. It has also side channel attack protections like DPA countermeasures or sensors against physical attack. It supports also secure debugging, so it can handle the debug port of all CPU you have in the system, making sure that all users are authenticated before opening the door of the debugger. And it has also a puff that enables to recreate the keys at every boot, and when the chip is down, all the keys disappeared. Okay, that's it.
Hi, I'm Jhalak Sharma from IIITB India. So till now, we saw different projects and ideas on how to increase speed, performance, accuracy, and decrease the power. But is your system error-free and reliable? So I'm working on a fault injection framework to study the probabilities of multiple bit flips. This study is important as it has significant impact on circuit reliability. So why RISC-V? Because people have worked on circuit level implementation. Together with RISC-V, we can work on architectural level and make all the RISC-V cores fault-free. I can tell you how to do it. Please come to the poster and we can discuss further. Thank you.
Thank you.
Hi everyone, my name is Fabian. I'm a PhD student here at ETH Zurich. As already teased this morning in one of the keynotes, we have manufactured Cosmodrome, which is a chip which features two 64-bit Ariane cores with extended set of floating point formats, which offer a very nice trade-off between energy efficiency and precision. The chip also offers a 32-bit special floating point accelerator, which gets you very high efficiencies. We have a poster on that in the poster section, so please come talk to us and let's have a discussion. Thanks.
Hi, my name is Charlie Su from Andis Technology. Today I'm going to talk about two things. First, Andis Custom Extension is a powerful environment for a domain-specific architecture for instruction extension. It just gets better with a new feature called Custom Port, which allow efficient RTL connection, so you can use it to directly connect to your RTL. So next, I'm going to talk about RISC-V Freestyle. We just announced it yesterday. So it including Andis Core N22, which is full feature, configurable with all the ecosystem supported. And its core mark per megahertz can go up to 4.0. And you can use it without upfront fee and just need, when you go production, just pay reasonable license fee. And it also comes with free download, full feature, and design IDE. And there's also optional support package, including online support, and also an HP platform IP. So you can come to our website, freestyle.andistech.com, or stop by our poster for more discussion. Thank you.
Hi, my name is Nicolas from OneSpin. So my poster is about formal verification of RISC-V cores, especially of CSRs, which are part of a bigger project. So the formal verification of the RISC-V cores, they are hard to verify, branch prediction, forwarding out of order, and formal verification is the only technology that can prove absence of bugs. There are different challenges, complexity issues, and it is hard to write good quality reusable assertions. And the OneSpin RISC-V integrity verification solution is uses a RISC-V ISA formalized in system Verilog SVA language, decouples microarchitecture details, enables 100% exhaustive formal proof for implementation of all instructions, enables verification of entire core implementation, and detects any extra functionality beyond the ISA specification. Also, at the poster, we can discuss more, and there is a list of issues we have been identified. So pay a visit to my poster, and we'll be glad to answer to any question you have. Thank you.
Thank you. Thanks. Okay, so first of all, thanks everyone for the poster session and adhering to the time. I think this is the first time in the history of our workshops that they actually went on time through the poster sessions. 1 minute early. So if everybody can get back here, we'll take a break now and head back at 3:20.